Welcome to This Explainer. Today, we're basically stepping into the shoes of a tech detective. We're going to investigate a hidden bottleneck that might be secretly ruining your AI's accuracy right under your nose. We're taking a magnifying glass to the foundational architecture of Retrieval-Augmented Generation to figure out exactly why your system might be failing to give you the right answers. Okay, let's dive right into this provocative question. Is your AI hallucinating because of how you cut up your text? Developers often just assume that throwing expensive, massive language models at their text fixes absolutely everything. But when an AI starts hallucinating or missing the point, the evidence actually points elsewhere. In fact, it almost always points directly to how your source documents were chopped up in the very beginning. Before we crack this case, let's establish our terms. Chunking is the process of breaking down large documents into smaller, manageable text segments for vector embedding and retrieval. It is the absolute foundational step of your pipeline. Honestly, it dictates the future performance of your entire system. If you get this wrong, no amount of fancy prompt engineering or pricey models is going to save your final output, because the AI simply won't have the right context to read from in the first place.
Here is our roadmap for solving this mystery together. 1. Busting chunking myths. 2. The double pass solution. 3. Matching size to embeddings. And 4. Debugging in the terminal.
Section 1. Busting chunking myths. We're pulling our first piece of evidence straight from the superlinked vector hub data. And spoiler alert, it completely flips a major industry assumption right on its head. So we intuitively expect complex AI-driven tools to win, right? But the data actually shows that the much simpler, naive sentence splitter, which literally just cuts text based on chunk size and overlap parameters, actually outperforms the highly complex semantic splitter across multiple datasets. There's no way, right? The advanced semantic method tries to break chunks based on shifts in meaning, but ironically, it ends up performing worse. This brilliantly illustrates exactly why the fancy semantic method fails. As the superlinked research points out, high semantic similarity measures can result from noise rather than meaningful similarities, because word embeddings basically encode the average meaning of a word. Since words constantly change meaning depending on context, relying purely on mathematical semantic similarity creates this weird mathematical noise. It forces the chunker to break the text at the worst possible times, separating thoughts that absolutely belong together.
Section 2. The double pass solution. So if classical semantic chunking gets easily confused by sudden shifts in text, like dropping in a math formula, a quote, or a block of pseudocode, how do we actually fix it?
The researchers at BitPeak tackled this exact problem and developed an ingenious semantic double pass algorithm. Traditional semantic chunkers just stop the moment they see a difference, like a code snippet. But check out step 2 here. This method looks ahead. If the chunk after the code snippet matches the chunk before it, it merges all three together. It's a brilliant maneuver that rescues highly relevant text snippets that usually just get orphaned. Talk about a lifesaver. Now, you might be sitting there thinking, well, I'll just use a powerful language model to analyze and group my text perfectly. Well, contrary to popular belief, you really don't need to spend an astronomical $29 per document using OpenAI's proposition-based chunking with GPT-4 just to get good context. Just look at this comparison. It's a massive win for the double pass method. When evaluating long texts, the BitPeak team found that double pass merging delivered higher correctness scores for absolutely zero cost, running locally via Spatie in just 16.7 seconds. Meanwhile, the GPT-4 proposition-based method took over 40 minutes and cost almost $30 for the exact same document. And get this, it statistically performed worse on long prose. Insane, right? Section 3. Matching size to embeddings. Drawing on some hard enterprise data from researcher Philip Art, we're going to uncover another crucial variable hiding in plain sight. We just talked about the method, but what about the actual physical size of the chunk itself? This research analyzed thousands of pages of SAP enterprise documentation to reveal that optimal chunk size is never static. It's actually intimately tied directly to your specific embedding model. For instance, if you use the E5 model, your sweet spot is around 750 characters. But if you switch to Google's Gemini text embedding model, you need massive chunks of 3,000 characters to get the best performance. Standardizing just one chunk size across all your projects? Yeah, that's a massive mistake. The crucial takeaway here is that you have to pair the right chunk size with the right model. When done correctly, dense retrieval consistently beats out traditional sparse baselines like BM25. In this enterprise study, Gemini took the top spot with an impressive accuracy of 0.846. But remember, That only happened when it was fed those larger 3,000 character chunks it absolutely craved. Section 4. Debugging in the terminal. Knowing that all these invisible variables, the method, the size, the embedding pairing, can completely ruin your RAG system, how do we actually fix them without ever leaving our coding environment? Enter RAGTY. This is the ultimate developer weapon. It brings all that invisible code right to the forefront of your screen so you can literally watch your chunks form in real time. It's a terminal-native tool that lets you visually debug your chunking pipeline completely offline, meaning your highly sensitive enterprise documents never ever have to leave your machine. You seamlessly move through this interactive workflow. You load your document, do a quick clean, and as you tweak the size and overlap sliders, the chunks re-render instantly. It literally highlights the overlap text between adjacent chunks right on your screen. This allows you to clearly visualize exactly how much context is being shared before you ever write a single line of vector database code. And instead of just guessing if your new chunks are better, RAG2E actually proves it. It can leverage a local LLM judge like Llama to grade your retrieved chunks against 5 industry-standard information retrieval metrics. We're talking hit rate, mean reciprocal rank, NDCG, recall, and precision. It scores the relevance of the text, giving you hard math on your results, ensuring your pipeline improvements are based on actual data, not just a gut feeling. Now, if you don't want to tweak those sliders manually, this tool completely eliminates the guesswork. The built-in optimizer will automatically sweep through up to 140 different size and overlap combinations in parallel. It tests them all against your queries and just hands you the math-backed winner. Once it finds the perfect strategy, you can export that optimal configuration directly into LangChain or Llama index format with just one click. Ultimately, all of this builds back to our core premise. Returning to Philip Art's enterprise research, they found a staggering 0.97 correlation between context precision and end-to-end accuracy. I mean, that essentially proves that your final AI answer is entirely at the mercy of your initial retrieval quality. Let's be real. If your chunks are bad, your AI is bad. Period. So if your retrieval quality determines your AI's accuracy, what are your chunks actually hiding? I really hope this explainer has empowered you to look at your text data a bit differently. Whether you're standardizing chunk sizes when you definitely shouldn't be, failing to do a double pass on technical documents, or just flying blind without visual debugging tools, there is always room to improve. It leaves you asking yourself, right now, what vital context is getting sliced out of your own invisible bottlenecks? Thanks for joining me on this deep dive into RAG chunking. Keep experimenting, and we'll see you in the next one.